Now let's use a graph of two functions to evaluate expressions, including compositions. Recall that the number inside the parentheses is an x value, and x is the distance from the middle horizontally. The result is a y value, and the y value is a distance vertically from the middle. So let's take this first problem, f of -4. Notice on my graph, I have two different types of lines graphed. I have f, which is a solid line. That's actually an absolute value function, you can see, because it's got that sharp bend in it. And then the other function, g, is represented by this dashed line here. It's really important to pay attention to that detail in the difference between them. It's not uncommon for confusion to happen because your eye jumps onto the other function, not the one you're supposed to be looking at. So if you need to use some colors to make it stand out, absolutely do that. There's nothing wrong with that. I'm going to put that F in pink right there to match my graph. And now I want f of -4. So I come over on my graph and I find -4 on the x-axis. So -4 here on the x-axis, and I'm going to take that value and find it on the function f. And that's really hard to see. Let's use the yellow. So -4, follow it up until it hits the graph of f. And then notice on the graph of f, if I follow that across, that's at y equals 1. So my y value here is 1. So I'm looking at this point right here, which is -4, 1 on that f function. X is -4, y is 1. Okay, let's look at a composition now. This first problem isn't really different than what we've done before as far as reading graphs go. But now we're going to apply this idea of compositions, which requires us to do that two-step process. So we'll start out with g of 0. 0's here in the middle, and I follow it up until I hit the g function. And the g function, remember, is the green diagonal line going down. I see that I'm hitting that value here on the g function, and that's at y equals 2. So g of 0 would be 2. That gives me a new x value that I then find, new x value, x equals 2. And now I need to follow it up. I'm going to use this bright blue. I'm going to follow it up until it hits the function f. And I see that it hits the function f at y equals 5. So f of 2 would be 5. And this 5 is my answer. I went through a two-step process. 0 on g, I find that it's 2. I then go to 2 on the x-axis, and I find on f that the y value is 5. See if you can try number 10 on your own, that two-step process. We'll write it out, g of f of -1. Find f of -1 first, and then plug it in for g, and then find your answer. Pause that video, resume when you're ready to check. I'm going to erase my markings on my graph. F of -1, -1 is going to be right here on my x-axis, -1 away from 0. I need to find f of -1, and I see that f of -1 is at 2. So f of -1 is 2. 2 becomes my new x value, and now I need to figure out what g of 2 is, and when I follow it up to hit g, I see that that y value is 1. Now let's try number 11, f of 0. We'll start out with f of 0, follow it up until you hit f. That happens at 3. 3 becomes my new x value, and now I need to follow it until I hit f again, and I hit f at 6. Now looking at a couple of examples of applications of composite functions, we have here a circular wave. A stone is dropped into a lake, creating a circular wave. The radius of the wave in feet after t seconds has passed is given by this function, r of t equals 2t. We also know from geometry that the wave's circumference is 2 pi r. So if we know the radius, we can plug the radius in and get the circumference. But our radius changes based on what value t is, how many seconds have passed. So in order to figure out the circumference at a particular time, we need to use that radius function. When we're talking things like practical applications, these types of functions are actually the building blocks for problems in college algebra, in trigonometry, and then into calculus. The first question asks us to evaluate C of R of 5 and interpret the result. So C of R of 5, R of t is 2 times t, so R of 5 would be 2 times 5, which is 10, and I could plug that in to my C function, and C of 10, 2 pi R, 2 pi times 10 would give me 20 pi, and we could get a decimal answer for that. I'm not going to. I like to keep it as pi. So we would say for the interpret your result part, that means you need to explain what that number is. What is 20 pi? Well, the circumference of the circular wave at, what does 5 represent? Seconds. Right. At 5 seconds is 20 pi. For part B, find C of R of t. This time we want the general function that tells us the circumference after a certain time has passed. So we'll start out C of R of t. We'll put in our R function, 2R. And then for C, we had 2 pi R, our old R, but now we need to take this expression in the parentheses and replace the old R with the new expression. Simplify this out, and we'll get 4 pi R for our circumference. Oh, I'm sorry. No. That's wrong. Not R. T. R of t is given by 2 times t. I need my answer to be in terms of t, not R. So there we go for the correction. And then looking at the volume of a balloon, we have a spherical balloon with a radius of r, and we have the volume function, 4/3 pi r. That's wrong. That's a typo. That is very much a typo. Volume of a spherical balloon, I apologize for this. Let's change that 2 to a 3. This is an exponent of 3. I'm going to blot that out. 2 pi r cubed there. Please make sure you change that in your notes if it's not corrected. 4/3 pi r cubed is the volume of a spherical balloon. Suppose the balloon is being inflated so that the radius in inches after t seconds is r of t equals cube root of t. And it's asking us to do a similar thing as before. First, evaluate the composition of the volume with the radius at 3 and interpret our result. So we'll start out with r of 3. R is the cube root of t, so r of 3 is going to be the cube root of 3. And then we'll put that into r of 3 cube root 3 into our volume function, 4/3 pi r cubed, but I'm going to put the parentheses in, just like we do with functions. And I see I have a cube root with a cube. Those are going to cancel each other out. 4/3 pi times 3. 3 and the 3 are going to cancel out, and this is going to give me 4 pi for the volume. So interpreting that result, the volume of the balloon at 3 seconds is 4 pi cubic inches, since we're talking about volume. And now we're going to find V of R of t. So instead of a number, V of R of t for part B. R of t is given by cube root of t, so we'll just take that function and replace it. And then cube root of t, our volume is 4/3 pi r cubed. Inside the parentheses is cube root of t, but the cube root and the cube cancel each other out. 4/3 pi times t will be our volume of the balloon.